Let's begin with a simple question. If the sun suddenly disappeared, how long would it take for Earth to notice? Most people say 8 minutes. That makes sense. Sunlight takes about 8 minutes to travel from the sun to Earth. So if the sun vanished right now, we would continue seeing it shining in the sky for 8 more minutes before darkness arrived. But now comes the uncomfortable follow-up. What about gravity? Would Earth continue orbiting normally for 8 minutes? Or would it instantly fly off in a straight line, suddenly released from the sun's pull? This question sounds simple, almost playful, but it reaches deep into the foundations of physics. For centuries, scientists struggled with it. To understand why, we have to step back to the 1600s and meet Isaac Newton. Newton gave us the first powerful mathematical description of gravity. According to him, every mass attracts every other mass. The Earth pulls on the moon pulls on the Earth, the sun pulls on all the planets. The strength of this pull depends on mass and distance. That's it. Clean, elegant, predictive. And it worked beautifully. Using Newton's equations, scientists could calculate planetary motion with astonishing accuracy. The paths of comets, the tides of the oceans, even the discovery of Neptune, all came from Newton's gravity. But buried inside his theory was something deeply strange. Newton's equations assumed gravity acted instantly. If the sun were to shift slightly, Earth would immediately feel the new pull. No delay, no travel time, no signal crossing space. Think about that. The sun is about 150 million kilometers away. Light takes 8 minutes to cross that distance. But in Newton's picture, gravity didn't need 8 minutes. It didn't need any time at all. It was as if the universe allowed invisible threads connecting every object, stretching across space, transmitting influence infinitely fast. Newton himself was uncomfortable with this idea. He famously wrote that the notion of one body acting upon another at a distance through empty space without something mediating that interaction was so great an absurdity that he believed no competent thinker could fully accept it. And yet the math worked. So physics lived with the discomfort. For over 200 years, gravity was treated as an instantaneous force. No one could measure any delay because the solar system moves slowly enough that any difference would be tiny. The planets follow smooth orbits. Nothing dramatic happens when the sun shifts slightly in its motion around the galaxy. From everyday experience, instantaneous gravity seemed harmless. But there was a quiet tension growing in physics, because in the 1800s, scientists discovered that light is not instantaneous. It travels at a finite speed, about 300,000 kilometers per second. Fast, yes, but not infinite. And that raised a dangerous question. If light has a speed limit, why wouldn't gravity? If information about the sun's light takes 8 minutes to reach us, why would information about its gravitational pull arrive instantly? The stage was set for a revolution. By the early 20th century, physics was standing on unstable ground. On one side, Newton's gravity had ruled for more than 2 centuries. It predicted planetary motion with extraordinary precision. Engineers trusted it. Astronomers relied on it. It was practical, powerful, and seemingly complete. On the other side, a new discovery was reshaping our understanding of nature. Light always travels at the same speed, no matter how fast you are moving. This strange fact emerged from experiments on electromagnetism in the 1800s, and it refused to fit inside Newton's universe. Enter Albert Einstein. In 1905, Einstein introduced special relativity. Its core message was simple but radical. The speed of light is the ultimate speed limit of the universe. Nothing with mass can catch up to it. No signal can outrun it. No influence can exceed it. This wasn't just about light. It was about causality, the order of cause and effect. If something could travel faster than light, then in some reference frames it could arrive before it was sent. Effects could precede causes. Time itself would lose coherence. So if the speed of light is the maximum speed for any influence, what happens to gravity? Newton's theory said gravity was instantaneous. Einstein's new framework said nothing could be. The two ideas were incompatible. Einstein spent the next 10 years wrestling with this contradiction. He realized that the problem ran deeper than just adding a delay. to gravity. The entire concept of gravity as a force acting across empty space had to be rethought. His breakthrough was not to treat gravity as a force at all. Instead, he asked a different question. What if gravity is not something that travels through space, but something that changes space itself? Imagine you are inside an elevator in deep space. If the elevator accelerates upward, you feel pressed to the floor. It feels like gravity, but there is no planet beneath you, just acceleration. Einstein realized that acceleration and gravity are locally indistinguishable. This became the equivalence principle, the seed of general relativity. From there, he took a bold leap. Mass and energy do not pull on objects through invisible forces. They curve spacetime. Spacetime is not just space. It is space and time woven together into a single fabric. Every event in the universe has both spatial and temporal coordinates, inseparable from each other. Mass tells spacetime how to curve. Curved spacetime tells matter how to move. That's the entire theory in one sentence. Picture a stretched rubber sheet. Place a heavy ball in the center. The sheet curves. Now roll a smaller ball nearby. It doesn't move toward the heavy ball because of a mysterious force. It follows the curved surface. This analogy isn't perfect, but it captures the spirit. In Einstein's picture, the sun is not pulling Earth with a force that shoots across space. The sun warps the geometry of spacetime around it. Earth simply follows the straightest possible path within that curved geometry. Now the crucial point, if spacetime itself changes, if the sun moves or explodes or disappears, those changes cannot propagate instantly. They must travel outward at a finite speed. And according to the mathematics of general relativity, that speed is exactly the speed of light. Gravity is no longer instantaneous. It is woven into the structure of spacetime, and any disturbance in that structure spreads at light speed, not faster. The universe, it turns out, enforces its speed limit everywhere. Now we arrive at the part that makes people uneasy. Even after accepting Einstein's picture, there seems to be a contradiction hiding in plain sight. You look at the sun in the sky. The light entering your eyes left the sun about 8 minutes ago. You are not seeing the sun as it is now. You are seeing it as it was. That's easy to accept. But gravity complicates the story. If gravity also travels at the speed of light, then the gravitational pull Earth feels should also be based on where the sun was 8 minutes ago. In other words, Earth should be responding to the sun's old position, not its current one. Now pause and think about that carefully. The sun is not standing still. It moves slightly due to the gravitational pull of the planets, especially Jupiter. It also orbits around the center of the Milky Way galaxy. So the sun's position is constantly changing, even if only a little. If Earth were always being pulled toward where the sun used to be, you might expect something strange to happen. The gravitational pull would always point slightly behind the sun's actual position. That backward pull should introduce a torque, a twisting effect on Earth's orbit. And over time, that torque should destabilize the orbit. Earth might spiral outward, slowly drifting away. But that does not happen. The solar system is remarkably stable. Planetary orbits are consistent over enormous timescales. Whatever gravity is doing, it is not lagging behind in a naive way. So it gives. At first glance, it looks like gravity must somehow be pointing toward the sun's current position, not its delayed position. And if that's true, it seems to imply that gravity knows instantly where the sun is now, which sounds suspiciously like faster than light communication. But this is where intuition misleads us. The mistake comes from imagining gravity as if it were like a beam of light or a rope being pulled tight between two objects. Light is emitted and travels through space until it hits your eyes. So we assume gravity must work the same way, emitted from the sun, traveling outward, tugging on Earth. But general relativity is subtler than that. When a mass like the sun moves at a steady velocity, the curvature of space-time around it is not simply pointing to where the sun was. The equations automatically include corrections for the motion of the source. These corrections are sometimes called velocity-dependent terms. An analogy may help. Imagine you are watching a boat move smoothly across a lake. The boat creates a wake in the water. The wake spreads outward at a certain speed. But the pattern of waves does not simply trail behind the boat in a straight line. The motion of the boat shapes the wave pattern in a way that reflects both its past and its ongoing motion. In a similar way, the gravitational field of a moving object is not a simple delayed arrow pointing backward. The structure of spacetime adjusts in a way that keeps stable orbits stable. Only when the motion changes abruptly, when there is acceleration, like in a collision of black holes, do true changes in the gravitational field propagate outward as gravitational waves. Those waves travel at the speed of light. So gravity does not move faster than light. But neither does it behave like a simple delayed signal pointing to the past. The full geometry of spacetime encodes motion in a way that preserves causality and keeps the cosmos from flying apart. If gravity doesn't act like a simple delayed pull from where the sun used to be, then what exactly is happening? The answer lives inside the mathematics of general relativity, but we can approach it without equations. The key idea is this: gravity is not a force being sent from the sun to the earth in the same way that light is emitted from a bulb. Instead, the sun creates a gravitational field, a structured curvature of spacetime that already fills the region around it. Think of temperature in a room. When you turn on a heater, the warmth doesn't exist only at the heater itself. The entire room develops a temperature distribution. If the heater runs steadily for a long time, the room reaches a stable pattern of warmth. Now imagine the heater slides slowly across the floor while continuing to produce heat at the same rate. The temperature distribution in the room doesn't lag in a chaotic way. The pattern shifts smoothly, adjusting continuously. The sun does something similar with spacetime. As long as the sun moves smoothly without sudden jerks, the curvature pattern around it evolves in a stable, consistent way. Earth isn't chasing a delayed gravitational signal. It is moving through a curved spacetime geometry that already accounts for the sun's motion. Here's another way to see it. In electromagnetism, a moving electric charge creates not just an electric field, but also a magnetic field. The two are intertwined. If you only consider the electric field and ignore the magnetic part, you get the wrong picture. Gravity has a similar subtlety. In Einstein's theory, a moving mass doesn't just create a simple static curvature. It creates additional components of spacetime curvature that depend on its velocity. These extra pieces modify how objects respond. When you include all of them together, something remarkable happens: the apparent aberration. The backward pointing effect you would expect from a delayed force cancels out for objects moving at constant velocity. So Earth's orbit remains stable not because gravity is instantaneous, but because the structure of space-time encodes motion in a self-consistent way. Only when the motion of a mass changes, when it accelerates, do genuine disturbances form in space-time. Those disturbances are gravitational waves. They are ripples in the geometry itself, and we have measured them. In 2015, scientists at LIGO detected tiny distortions in spacetime caused by two black holes colliding more than 1 billion light years away. The ripples stretched and squeezed space by a fraction of the width of a proton. These waves traveled at the speed of light. Later observations, including a neutron star merger detected in both gravitational waves and light, confirmed that the two signals arrived almost simultaneously after traveling vast cosmic distances. If gravity propagated faster than light, we would have seen a measurable difference in arrival times. We didn't. The universe obeys its speed limit with precision. So the mystery dissolves, but only if we abandon the old mental picture of gravity as a rope pulling across emptiness. Gravity is not a delayed tug. It is the evolving shape of spacetime itself, and that shape changes in a way that respects the cosmic speed limit at every step. Expanded fast part 500 words and remove all narrator headings and brackets. Now we come to the experimental turning point, the moment when this stopped being a purely theoretical debate and became something we could measure. For decades, gravitational waves were just a prediction written in Einstein's equations. General relativity said that if massive objects accelerate, not just move smoothly, but but accelerate, they should produce ripples in space-time itself, not ripples in matter, not ripples in energy fields, ripples in the geometry of reality. But these ripples would be incredibly weak. By the time they reached Earth from distant cosmic events, they would stretch and squeeze space by less than the width of an atomic nucleus. That sounds impossible to detect. And yet in 2015, the observatory known as LIGO measured exactly that. Two enormous black holes had collided about 3 billion light years away. As they spiraled into each other, they accelerated violently, disturbing space-time. Those disturbances radiated outward in all directions at the speed of light. When the waves finally reached Earth, they slightly changed the lengths of LIGO's laser arms. One arm became a tiny bit longer, while the other became a tiny bit shorter. Then they reversed. The distortion was smaller than 1/10,000th the diameter of a proton, and yet it was measurable. This was not just a confirmation that gravitational waves exist. It was a confirmation that changes in gravity propagate at light speed. But the decisive moment came 2 years later. In 2017, LIGO and its European counterpart Virgo detected gravitational waves from a pair of neutron stars merging. At almost the same time, telescopes around the world detected a burst of light, gamma rays, from the same event. The gravitational waves and the light had both traveled about 130 million light years to reach us. If gravity moved faster than light, even slight, it would have arrived noticeably earlier. If it moved slower, it would have arrived later. Instead, they arrived within about 2 seconds of each other after traveling for 130 million years. That difference is astonishingly small. It tells us that gravity travels at essentially the same speed as light to an extraordinary degree of precision. So experimentally, the case is closed. Gravity does not outrun light. And yet the conceptual discomfort remains for many people, because we are still tempted to imagine gravity as something being sent from one object to another, like a message in transit. The experiments show that when space-time itself is disturbed, when massive objects accelerate violently, those disturbances move outward at light speed. But when objects move smoothly, their gravitational influence forms a stable pattern that does not behave like a delayed arrow pointing to the past. The measurements confirm what Einstein's equations had quietly insisted all along: the universe enforces its speed limit not just for light, but for gravity itself. And that realization reshapes how we think about influence, causality, and the very structure of space and time. Even after all the equations and all the experiments, many people still feel uneasy about this idea. If gravity travels at the speed of light, why does it feel instantaneous? Why doesn't the delay show up in obvious ways? Why don't planets wobble unpredictably? Because they are responding to slightly outdated information. The difficulty isn't in the physics anymore. It's in us. Our brains did not evolve to understand curved space-time. They evolved to throw spears, judge distances, and predict the motion of visible objects. We think in terms of pushes and pulls. When something moves, we imagine a force acting on it. So when we hear that the sun affects the earth through gravity, we instinctively picture something like an invisible rope connecting them. If the sun moves, the rope must shift. If the rope has a finite speed, it must lag behind. And if it lags, it must pull from the wrong direction. That picture is simple. It is also wrong. In Einstein's framework, Earth is not being tugged by a rope. It is following the straightest possible path in a curved 4-dimensional geometry. The word straight here is deceptive. In curved space-time, the straightest possible path, called a geodesic, can look curved to us. Earth's orbit around the sun is not the result of a sideways force constantly pulling it inward. It is the natural motion of an object moving through curved space-time. This is deeply unintuitive. To see why, imagine you are walking on the surface of the Earth. You start at the equator and walk straight north. You think you are moving in a straight line. Now imagine someone else starts at a different point on the equator and also walks straight north. Eventually, both of you meet at the North Pole. From your perspective, neither of you turned. You both walked straight, yet your paths converged. That happens because the surface of the Earth is curved. Space-time works similarly, except the curvature is not in ordinary space alone. It involves time as well. Massive objects like the sun curve not only the spatial dimensions, but the temporal dimension too. This means that what we call falling toward the sun is partly a result of how time flows differently in curved space-time. Earth is always moving forward in time. The curvature of space-time bends that forward motion into what we interpret as an orbit. When you think this way, the question, how fast does gravity move, begins to shift. Gravity is not an object traveling through space. It is the structure of space-time itself. Asking how fast gravity moves is a bit like asking how fast the shape of a valley moves. The valley simply exists. But if there is an earthquake that reshapes the valley, that change travels outward at a certain speed. In space-time, that speed is the speed of light. The struggle we feel is not a failure of physics. It is a mismatch between ancient neural wiring and a universe far stranger than survival required us to understand. We are trying to picture a four-dimensional geometric reality using a brain designed for hunting and gathering. And yet, remarkably, the mathematics works. That is perhaps the most astonishing part. Now we arrive at the edge of what we truly understand. General relativity has passed every experimental test so far. It predicts planetary motion, black holes, gravitational waves, the bending of light near massive objects. Its accuracy is almost unsettling, and yet we know it is incomplete because there is another theory that describes nature with equal precision: quantum mechanics. Quantum mechanics governs the very small, atoms, electrons, quarks, the fluctuations of fields in empty space. It tells us that energy comes in discrete packets. It tells us that uncertainty is built into the structure of reality. It tells us that particles behave like waves and waves behave like particles. It works astonishingly well, but when we try to combine quantum mechanics with Einstein's theory of gravity, something breaks. In quantum theory, forces are mediated by particles. Electromagnetism has the photon. The strong force has gluons. The weak force has W and Z bosons. If gravity fits this pattern, it should have its own quantum particle, often called the graviton. We have never detected such a particle. More importantly, when physicists attempt to quantize gravity in the same way as other forces, the mathematics explodes into infinities that cannot be easily removed. The theory becomes non-renormalizable, which is a technical way of saying it loses predictive power at very small scales. This tells us something profound. General relativity treats space-time as smooth and continuous, like a perfectly polished surface. Quantum mechanics suggests that at extremely small scales, around the Planck length, reality may be grainy, fluctuating, even turbulent. If space-time itself is subject to quantum fluctuations, then our classical picture of gravity as smooth curvature cannot be the final word. Some modern approaches attempt to go deeper. String theory proposes that fundamental particles are tiny vibrating strings, and gravity emerges naturally from their vibrations. Loop quantum gravity suggests that space-time itself is made of discrete loops woven into a network. Other ideas propose that space-time might emerge from patterns of quantum entanglement. In some of these frameworks, space-time is not fundamental at all. It may be an emergent phenomenon, like temperature emerging from the motion of microscopic atoms. If that is true, then asking, how fast does gravity move, may eventually become like asking, how fast does temperature move? The question only makes sense at a certain level of description. At a deeper level, the familiar notions of space and time might dissolve. This is not speculation for its own sake. There are real puzzles driving it. Inside black holes, general relativity predicts singularities, regions where curvature becomes infinite. At the Big Bang, the equations also point to an initial singularity. These infinities signal that the theory is being pushed beyond its domain of validity. Something else must take over. We do not yet know what that something is, and that is an honest answer. The speed of gravity, as described by Einstein's equations, is the speed of light. Experiments confirm it, but whether space-time itself is fundamental, or whether gravity emerges from deeper quantum principles, remains one of the greatest open questions in physics. We stand in a strange position. We understand gravity well enough to detect ripples from colliding black holes billions of light years away. And yet we do not fully understand what gravity ultimately is. That tension between precision and mystery defines the frontier of modern physics. There is a quiet philosophical shift hiding inside all of this. When people first hear that nothing can move faster than light, they treat it as a technical constraint, like a cosmic speed limit sign posted somewhere in the universe. Light just happens to be very fast, and nature won't let you go faster. But that interpretation is shallow. The speed of light is not merely the speed of light. It is the speed at which cause becomes effect. It is the speed at which structure in the universe can influence other structure. When we say gravity travels at the speed of light, we are not saying gravity is racing alongside beams of radiation. We are saying that changes in the structure of space-time obey the same causal architecture as everything else. And that architecture is woven into reality itself. If gravity were instantaneous, something profound would break. Imagine a universe where influence had no delay. Move an object here, and the entire cosmos responds immediately. There would be no meaningful separation between here and there. Distance would lose operational meaning. The distinction between past and future could blur in certain frames of reference. Causality, the orderly chain of events, would become fragile. The finite speed of gravity protects the coherence of time. It ensures that events unfold in a structured way, that effects follow causes within the light cone of space-time. The geometry of space-time is built so that signals, whether electromagnetic or gravitational, cannot outrun this fundamental limit. And this leads to a deeper realization. We often imagine space as an empty container in which objects move, and time as a universal clock, ticking the same everywhere. That picture is comfortable. It feels solid. But relativity replaced that comfort with something more radical. Space and time are not passive backgrounds. They are dynamic participants. They stretch, bend, ripple, and interact with matter and energy. You are not moving through a static stage. You are part of the stage. The atoms in your body curve space-time, though only slightly. The Earth curves space-time more strongly. The sun curves it dramatically. Black holes warp it so intensely that even light cannot escape. Every object is both actor and sculptor. And when the sculpting changes abruptly, when massive objects accelerate violently, the news spreads outward at light speed as gravitational waves. The structure of reality updates itself locally, step by step, never skipping ahead. This changes how we see distance. When you look at a distant star, you are looking into the past. When you feel Earth's gravity, you are participating in a space-time geometry shaped by mass, energy distributed across the cosmos. There is no universal, no, connecting all points instantly. There is only a web of causal relationships, expanding outward at a finite speed. The idea that gravity might move faster than light turns out to be an illusion born from outdated intuition. But chasing that illusion forces us to confront something far more unsettling and beautiful. The universe is not a collection of objects interacting inside space and time. It is a single, dynamic space-time structure within which objects and events are patterns. And once you begin to see reality that way, the question is no longer how fast gravity moves. The question becomes what space and time truly are, and whether they are the final layer of the story at all. Let's slow down and look at the deeper shift this forces on us. When you were a child, you probably imagined the universe as a big empty box. Inside the box are stars, planets, dust, light, and you. Time is like a universal clock hanging on the wall of that box, ticking the same everywhere. That picture feels obvious, but relativity quietly destroys it. There is no universal clock hanging on the wall of the cosmos. There is no rigid container called space, sitting there independently of what's inside it. Instead, space and time form a flexible structure that responds to matter and energy. This is not poetry. It is measurable. Clocks on GPS satellites tick at a slightly different rate than clocks on Earth's surface. Because of both their speed and the weaker curvature of space-time at their altitude, if engineers ignored relativity, your phone's map would drift by kilometers each day. So space-time is not philosophical decoration. It is operationally real. Now connect this back to gravity. In Newton's world, gravity was something added on top of space and time, a force acting within them. In Einstein's world, gravity is inseparable from space-time itself. To ask how fast gravity moves is to ask how fast geometry can change. That's already a strange sentence. Geometry changing. We're used to geometry being eternal in abstract triangles, circles, straight lines. But in general relativity, geometry is physical, it bends. It evolves. It carries energy in the form of gravitational waves. And those changes propagate at the speed of light because the structure of space-time itself enforces that limit. Here is the philosophical twist. The speed of light is not about light. It is about the conversion rate between space and time. It tells you how much time must pass for a certain amount of spatial separation to be bridged by any causal influence. It is a property of the geometry of reality. Once you see that, the universe stops looking like a collection of things connected by forces. It starts looking like a single, interconnected fabric whose internal consistency defines what can and cannot happen. Nothing outruns light, not because of a cosmic rule imposed from outside, but because space-time's structure makes it impossible. And gravity, being geometry, obeys that structure automatically. But now we reach the horizon of ignorance again. We still do not know whether space-time is fundamental. Some theoretical work suggests that space-time might emerge from more primitive ingredients, perhaps quantum entanglement patterns or microscopic degrees of freedom we have not yet discovered. If that is true, then light speed may not be a fundamental limit in the deepest layer of reality. It may be a derived limit, the way the speed of sound is a limit inside air, but not outside it. That possibility is both thrilling and destabilizing. It suggests that what we call space and time could be effective descriptions, valid at large scales but incomplete at the smallest ones. So here we stand. We know gravity does not move faster than light. Experiments confirm it. Theory demands it. But in trying to answer that question, we discover something far more profound. The universe is not built the way our instincts suggest. It is not objects first and space later. It is structure first, a dynamic space-time web, and objects are stable patterns within it. When you look up at the night sky, you are not staring into empty space sprinkled with lights. You are looking into a vast, evolving geometry where every star, every planet, every black hole is shaping the very stage on which existence unfolds. And the fact that gravity respects the speed of light is not a limitation. It is a clue that causality, space, and time are woven together so tightly that to change one is to change them all. Once you see that, the universe no longer feels like a machine operating in space. It feels like space itself is alive with structure, and we are part of its unfolding pattern.